It's all about sizes. This article was written in 2003 to grasp how minute the oil film clearances formed in machinery are. The article was picked up and published in the Machinery Lubrication magazine 2007, a couple of years later published in the Industrial Electrics magazine. In 2025 it was presented for the VANS conference in New Zealand. Lubrication film thickness is important. Understanding the actual clearance size, thickness, depth of lubrication films formed between machinery components is essential for adequate lubrication. Providing adequate lubrication is crucial for acceptable machine reliability and economic success. Lubrication film thickness is a deciding factor for contamination control, filtration requirements, and determining the lubrication regime. Understanding size, microns and human perception. Lubrication film thickness is measured in microns, where 1 micron is 1/1,000,000th of a meter or 1/1000th of a millimeter. Putting this in perspective, a human hair measures 70 to 100 microns in diameter. The lower limit of human visions is 40 microns, about half the thickness of a human hair. The lower limit of human fingertip sensitivity is 15 microns. Many typical lubrication films are much smaller than what we can see or feel. Typical lubrication film clearance is formed in machinery. Different applications form varying oil film thicknesses when operating. Examples include gears 0.1 to 1 micron, roller and element bearings, roller or ball 0.4 to 1 microns, journal bearings 0.5 to 25 microns, oiling rings on shaft typically 0.5 to 5 microns, hydrostatic bearings, big end bearings in our vehicles 2 to 100 microns, hydraulic servo valve ball to sleeve 1 to 4 microns. There are many tight clearances areas in engines that operate with less than 1 micron lubrication film thickness. Examples include piston rings to bore, rockers to cam lobes, all having less than 1 micron or below the limit of human vision. Normal lubrication film clearances formed in applications when operating. This slide displays typical lubrication films formed in machinery when operating. Observing the chart, we can see the majority of these applications form lubrication film clearances below the limit of human vision or fingertip sensitivity. Impact on maintenance. Without understanding the lubrication film thickness, maintenance often focuses on preventing visible contaminants greater than 40 microns from entering the system. This approach can miss the smaller, more damaging particles. If unfiltered environmental airflow access is permitted into lubricated areas, the normal lubrication film thickness formed in the majority of machinery cannot protect the application from hard particle damage. Understanding the lubrication film thickness will display that many machine component clearances are far smaller than the limit of human vision. The most damaging size range and contamination entry points. R&T's reliability studies indicate that fine, hard, airborne environmental contaminants in the 2 to 20 micron size range cause 80 to 90% of abnormal wear in oil and grease lubricated machinery. Contamination entry points for engines, compressors, blowers, usually via the clean air induction system plus sump breathers. For gear drives, transmissions, hydraulics, usually via breather vents. For grease system, often caused by pulse-type greasing relubrication methods in the contaminated environments, allowing dirt into the lubricated area due to voids left as the grease channels away. Understanding airborne particle contamination. This chart shows the distance and time fine particles remain suspended in normal airflow. The most abnormal wear is caused by hard contaminating particles in the 2 to 20 micron size range. This is referred to as the medium mesoscale size range. Particles in this range are below the limit of our vision. The size range from medio-mesoscale down to fine microscale encompasses the normal lubrication film thickness. Even the larger particles in this range can remain suspended for a kilometre or more. This type of environmental contamination will be continual. Contamination in this size range should always be expected to be present. The Sydney dust storm, 23rd September 2009. The two street images display the level of airborne contamination in central Sydney as the dust storm was blown through the city. The particle concentration level reached 15,000 milligrams per cubic metre. Sydney normal air cleanliness would be 70 milligrams per cubic metre. The car images display the deposition that was uplifted off the bonnet using a tape sample and inspected under the microscope. These micro images are taken at 500 times of the dust picked up off the car bonnet with the tape sample. The vertical red lines either side of the lower set of images represents the lubrication film thickness at 500 times. The glowing crystalline shapes are silica lightly fluorescing under the microscope's polarized light. Note the large difference in size between the crystals and the lubrication film thickness. Displaying these crystals would cause serious damage if able to gain ingress into machinery. This map of the Sydney dust storm displays the vast distances this contamination was carried on the airflow. This reinforces that airborne particulate contamination has to be expected anywhere at any time. The contamination cycle driven by temperature changes. Air expands and contracts approximately 10% by volume for every 10 degrees temperature change, depending upon environmental variables. As the system cools, it draws in air and airborne contaminants into the lubricated area. The air and the contaminants then intermix with the lubricant. As the system heats up again, the air expands, but only the air escapes, leaving the airborne contaminants behind. This heat-cool cycle continually increases the amount of fine particle ingress with every thermal cycle, forming a homogeneous mixture of environmental dirt, metallic wear debris, and damaged lubricant. Add water to this mixture, and then erosive wear also develops. Maintenance best practices. Cleanliness is key. The rule of thumb is that it's 10 times less expensive to keep contamination out of oil lubricated areas than it is to try and remove it later by filtering. The 2 to 20 micron range is the same size as the germs that make us sick. If we can apply the same cleanness we'd expect for our food surfaces to our oil containers and oil contacting surfaces, we can control a major source of contamination. The lower left image displays incorrect storage for new lubricants, contrasted with the lower right image of the correct storage of new lubricants. Maintenance best practices. Airborne contamination has to be expected regardless of whether indoor, outside, countryside or city. Therefore, correct proactive maintenance on breather filters and air induction filters is essential to control airborne contamination. R&T's breather filter research on applications that continually thermally cycle displayed that it only took 3 months for fine dirt to work through the media. The use of filter carts are efficient for controlling contamination. The advice is that all new lubricants are filtered at 5 microns when transferring lubricants or oil changing. Consider that large engine oil filters remove all contamination, preventing oil analysis from detecting abnormal wear. Performing a filter debris analysis on an engine oil filter has proven to be an accurate method of determining abnormal wear. The filter debris analysis identifies all contaminants, including the critical 2 to 20 micron size range, gaining entry into the engine.